Right enough. Thank you so much. I appreciate having the opportunity to be here with you today to cover this topic. It's exciting. We spent a long time working on this, and we've learned some good things along the way, and that we're excited to share with you today. So, all right, next slide, and go next here. Okay, is our intro slide. All right. I just want to orient you to that we have two different variable speed limit zones within Utah, several miles long. So they're both regulatory. This one is just east of the Salt Lake City metro area in the mountain terrain that goes up towards Park City. It's about 12 miles long, and we have another one that's next slide. It's in kind of our south central rural Utah area, interstate, where the speed limit's normally 80 miles per hour in this area. But we have a high mountain pass that comes up out of the desert floor up into a little bit of a range that sees a lot of weather activity that's different than the open valley area. So this was a needed area for a corridor there. So this is the two that we've mostly have our discussion centered around today. So next slide. Going back to the Interstate 80 corridor, this one, we had a number of instruments, devices already set up in the corridor. We already had ATMS and cameras, sensors, all that through the corridor. So it was very easy to bring in our VSL into that corridor. But we've also had to make some enhancements to how many devices we had there, since the placement of those devices weren't set there for the purposes of having a variable speed limit system. We brought the variable speed limit system years later, so we had to fill in some gaps and add some weather information and some detector information for supplemental information that we needed to do the calculations required for the speed adjustments. So as you can see here, we have quite a number of devices there. One significant part of this is the bottom bullet there, the elevation range change. The Salt Lake Valley floors in the 4,000s range. Up on the benches, it starts to creep up towards 5,000. As you enter the VSL corridor, you gain a little over 2,000 feet in about 10 miles or so. And then it peaks down on the other side for the rest of the corridor coming out of that canyon. So next slide. All right, a little bit more on the zones here. So we originally had this as where the region traffic engineering staff would change the speed limit based on their observations of looking at camera images, looking at speed data, and they would make a determination. So the zones were broken up just in a couple areas. But then once we went to automation, we brought the number of zones, increased them, basically bringing them much smaller segments where we can change the speed limits. So basically, it's every speed limit sign can be different from the one downstream of it. Now we have some parameters to have it smooth, so we don't have huge breaks in that change. But we went through a pretty significant change from our first variation of the speed limit system to bringing in more automation components to that. And what happens there is that we're all the traffic monitoring stations there are where we're picking up the speeds from travelers on the roadway that are already there, and they're helping us determine what the speed should be. We kind of call that voting for the speed. So that helps the algorithm figure out what we should be posting on the upstream sign of that zone. All right, next slide. All right, this is the little snapshot down in our south central area as well. Not as many devices, not as long in length, but again, another elevation rise. We're a little bit higher in elevation on that plateau, but then it does rise up sharply 1,000 feet. And sometimes that's a significant difference in the weather. You may have a cloud ceiling just above you that's maybe just lightly raining, but you go up a little bit in elevation around that range, you may now turn into snow or ice in those situations. So this is why that was applied at this location. So next slide. A little bit of snapshots of what there's a couple photos piled on top of each other. They're supposed to fly in, but that's okay. This is a PDF version of the presentation. But if you've ever been in that kind of situation, daytime or nighttime, it's difficult. It's white knuckle moments where you're trying to just navigate this corridor. You're trying to get somewhere. If you had a choice of not to be there, maybe that's your better choice. But sometimes people still have to get through the corridor. Helping them understand what those travelers downstream are doing with their speed is helping us make the calculations on the speed as they're entering the corridor. So they know how to target their speed if they're unsure of the situation they're dealing with. It just helps reinforce where they ought to be trying to find their target speed for what's lying ahead. Next slide. Real quick, I'm not gonna go through this point by point, but about 10 years we've been working on this technology. Went through a couple rounds. I mentioned our automation development, and then the exciting part about this, I want to give time to Cody after I'm done here to talk about the weather aspects of how we use weather information to change the speed limit. But we've enjoyed having this experience and time to develop and improve steadily through the life cycle to date. And then we just recently brought online the I-15 Baker Canyon. Now, one thing just to note there, that took a longer time to commission and integrate. That was in a corridor that had nothing. Like, it's far away from any power sources. Communication was not readily available. In contrast to that, to the Interstate 80 corridor, where we already had a significant ATMS instrumentation infrastructure, it was easy to bring that in within a year's time versus taking a little bit longer to develop all the components out in a very desolate area of the state. So and we just had our go live for the Baker Canyon this past winter. So we've only had about half a winter, and it was kind of a lighter winter than usual to round out our experience with that. So we just kicked off a consultant to look at some machine learning. One of the challenges with that is that, in those times when there's not a lot of traffic on the roadway or in the wee hours of the night, it's kind of hard to get enough of a sampling of where to place the speed on that in an algorithm. So we are exploring that. We'd love to have a future time to talk about that, but we're just barely starting that discussion now. Next slide. So how does UDOT get to make these changes? So when people consider speed limits, and Les may have alluded to this in a number of different ways already, is each state is going to have their own statutes or code or laws or whatever to help start that conversation about where do we get to do that. In Utah, we enjoy a lot of flexibility in how we do that. Basically, go ahead and hit the next slide. The code gives us the UDOT the authority to make this speed changes based on weather conditions, a number of other things, but weather conditions and other safety factors. So next slide. And instead of reading the small print there, that I just showed a sample of that, but here's more of the details where we can do that, where we have to have some kind of a study that helps determine that. So we can't do regular speed studies that you do like on arterial corridors with traffic counts and evaluations and take days and weeks to figure out what you're going to change the static speed sign. This has to happen within minutes. So the process we go through is more of an engineering design process in real time. So next slide. So in reference to how we can do that in our state law, it gives us that authority to do that. Next slide. So this is out of the manual on uniform traffic control devices. There's two sections in there to discuss engineering study and the procedures that we're talking about here is the application of procedures and criteria established by the engineer. So we have an engineering team that reviews this and decides how this process is going to work. So that's our interpretation of how we're applying that authority to make that determination in real time for traffic speed limits. Okay, next slide. So challenges I've mentioned before. So in Utah, we subscribe to the prima facie speed law, or the basic speed law as it's also referred to, which is basically whatever is reasonable and prudent for the prevailing conditions. So we have to basically take samples from what the population is deciding what is safe for them to navigate that corridor, and we average that and come up with some kind of a number that's going to say that should be the speed that other people should follow. So that's why we call it voting for the speed. They're basically casting their vote when we collect that data sample from a sensor. That's their choice of what they think should be the speed. So but the sampling size is impossible to have a statistically significant sample size because it's going to change every 3 to 5 minutes. We may only get a dozen, maybe 100 on a busy day through a corridor during a few minutes interval. So we have to have we have to be comfortable with how to do that, make that change within a small sample size. Okay, next slide. And we also anticipated that we don't want to get stuck in the records request process. We basically publish on our website all of the commands for each of the signs out there that give the speed to that sign. Now we can't prove what was posted on the sign. We can only demonstrate what was given from our TMS software to give that instruction to the sign. So highway patrol or citizens or anybody that want to do any research can go to this website link. They can download, they can pick the signs they want. They can export this into a file, a CVS file or a PDF. And we don't get involved in the records request process. We just make it available to anybody. So next slide. All right, so next I want to turn it over to Cody Oppermann. He's our weather program specialist, and he's going to talk more about the recent version that we've come through with the changing the speed based on weather parts only. We had the I-15 section of that. We wanted to be able to lower the speed based on weather conditions prior to travelers responding to that. So I'll let Cody discuss the rest of that.
Yeah, so as Chris mentioned, wanted to see how we can kind of integrate RWIS into this. I think most states, you can go ahead to the next slide, utilize RWIS for their VSL system. So we've talked about initially when we did manual changes of the VSL speeds, the operators or engineer who was operating it looked at weather data, but most of that manual transition was delayed. There was pretty good latency. And then the automation was solely based off speeds, as Chris talked about. But we wanted to see what can we do with the RWIS data to make to see if we can improve things. So we decided that when weather is coming in, we wanted to get speeds lowered before they have to start to react to the changing weather conditions. So what we decided here is we see some variables indicating weather's coming in. We'll lower that speed limit ceiling, as we'll call it, down 5 miles per hour in Parleys, which we haven't initiated yet, but hopefully this winter we'll have that going. And then 10 miles per hour on the I-15 section, since it's a higher speed limit there. And then after that speed limit ceiling, then you get the vehicles voting, which drops the speed further. But then, so basically the whole idea with the RWIS here is just to catch people initially and get them to slow down. Next slide. And so there's 5 different kind of things we look at. And I think I was looking at Wyoming slides and they kind of do a similar thing. And I think other states do for certain types of weather scenarios where we look at, and I'm going to go quickly through this, but we look at standing water based off, you can see a sample RWIS tower here with the different instrumentation, what's being used. But if there's water on the road of a specific value, low visibility, high winds, if the road grip or coefficient of friction is deteriorating, and then a complicated algorithm for snowfall rate. But if we start to see any of those, observations showing deteriorating conditions, that will trigger this lowering of speed, the speed limit ceiling, if you will. We originally had 10-minute observations. To reduce latency, we went down to 5-minute observations. And because we want to see a deterioration in the conditions, as well as kind of if there's any one-off bad observations, we kind of weed that out. Most of these conditions we take 2 subsequent observations to show a deterioration or that conditions are bad enough. And I think I'll gloss over the next 4 slides here if you want to skip through. You can kind of look at these flow charts for what initiates a weather event. Wind gust, we trust that data enough. If there is a strong wind gust for one observation, that will trigger the VSL. Both of these corridors aren't traditionally a high wind or crosswind problem, but we have that in there just in case. So next slide. And then at the end of a weather event, as conditions start to improve, we notice people their speed starts to kind of dramatically increase, but we didn't want to say, hey, don't go full speed just yet. There still could be problems in the corridor, weather still being an impact. So all these variables, as you've seen here, are like we can tweak them based off the zone that we're in. I'll also go back and say we at least have a full RWIS station in each zone, or at least a road sensor to determine some of these variables. And then that'll impact the zone that it's attributed to, and then can filter if it's just the one zone that's being impacted, then you'll go back to normal speeds on the zones adjacent, but that'll at least trigger that the entire corridor could have weather problems. But anyway, so at the end of a weather event, we need to make sure all the variables come back to a safe condition for speeds to go back up to the normal speed limit. Next slide. I was going to show a quick example from last winter. We noticed an issue with our algorithm that we need to go back and fix in the I-15 Baker Canyon section. This graph real quick shows that boating speed. That's kind of a complicated thing, I think, how we come up with that. But and then the orange line is kind of what that ceiling speed should have been, and we should have triggered an event sooner and ended sooner. But anyway, next slide. So a little bit, I took an example from a long time ago of how this should have operated. You can see here, this was back in 2020, but a storm that happened in November. You can see the weather variables there. I've highlighted some of those variables where we're starting to see an uptick in the snowfall, and coefficient of friction started a light decline. And then this chart on the upper right shows the aggregate speed across the lanes there on this eastbound zone. Next slide. I had to interpolate the RWIS data since we were taking 10-minute observations, but let's say that if it was 5-minute observations here, you see the snowfall rate ticked up a little bit more, road grip stayed the same, but we haven't triggered any of the thresholds from our algorithm yet, but speeds are still elevated. Next slide. Again, conditions are deteriorating, but not quite yet. And then next slide. We've hit our thresholds for a weather event to begin. The aggregate speed there is 63. So we've, at this point, would have theoretically lowered the speed to 60 and got people aware. And you can see in the camera image how the storm is picked up. And we also, I didn't mention this, but we also are looking at these 2 subsequent observations in case you had like a passing flurry over a course of 5 minutes that we didn't want to pick up on, in case the weather data return back to a better state. So I had to show deteriorating condition, and this is how this would have worked theoretically. Next slide. There's some various groups doing research here, and then Chris mentioned the machine learning project that we're doing, so I won't spend time here. Next slide, and then there's our contact information if you have any questions.